Unit 3, Lesson 6, Connecting Similarity and Transformations. So in 6.1, we have dilation miscalculation. So they're asking straight up, what's wrong with this dilation? Why is GHFE not a dilation of ADCB? Well, go ahead and pause the video, come up with your own ideas and reasoning, and then unpause it and we'll take a look at it. All right, so hopefully you pause the video and you realize something horribly happened here. You have a rectangle dilating into a square, or appears to be a square, right? We don't know about the congruencies of these sides, but obviously the two figures do not look similar. So they don't look similar. I did teach you dilation, and I did talk about going point by point to being able to backtrack where maybe your center of dilations occurred. Notice when I do that from E mapping onto B and F mapping onto C, right, we get this whole new center of dilation. So the original center of dilation was point P, but as you can see, something horribly went wrong because we have two centers of dilation. So we have two centers of dilation. That's probably a oopsie daisy indicator. I also noticed that EG to AB or BA did not change, right? It looks like it stayed the same, which implies the scale factor was just 1, while on the other hand, EF looked like it definitely got a scale factor of probably a half, right? Because it got smaller, at least half the length. So what's wrong with this dilation? One answer. You have two centers of dilation. Also, don't have a universal or constant scale factor, right? Because the blue sides, let me highlight them, look like they stay the same. Meanwhile, the red sides definitely went through some kind of scale factor, maybe a half, right? Something like that. So the blues stayed the same, but the reds did not. So that's an indicator that the scale factor was not constant for all the side lengths. All right, if you come up with any others, definitely let me know. But yeah, that'd be a good reasoning right there on what happened and what went wrong. All right, so this card sort would normally be applied in class. So these would be cut out, and you would basically categorize or identify whether these objects or these figures on each card are congruent, similar, or neither congruent nor similar. So if you look at card sort 1, we have two triangles here, right? We have this larger triangle, and then we have this smaller triangle. The implication here, it looks like it's going through some kind of dilation, right? And notice how each side appears to be parallel or collinear, right? So these two figures, I would say, are similar, okay? Because both those two triangles look to be very much the same angle, right? It looks like you have, let me clean this up a bit. Both triangles share the same angle here, right? This angle is definitely the same, 90-90, and that implies that since those two angles are congruent, then angle P and angle Q there also have to be congruent. Okay, so their angles didn't change at all, so I would say they are similar. The lengths are definitely different, right? So lengths are different, angles are the same. So that would be, so lengths are different, angles are congruent, right? So that's a good indicator that we're probably looking at a similar situation there. All right, since lengths are different, angles are congruent. All right, if we look at card sort 2, wow, okay. They look like they're squares to squares, right? In fact, I noticed that what times 3, right? What scale factor is being applied for 3 to become 12? 4, right? And the markings here for congruency tell me that that's the case for every side, right? So these are definitely similar, definitely going through a dilation, okay? Because we know the scale factor right there is being applied across the board. Even the angles are congruent, right? So lengths are different, angles are congruent, so I would say similar. So similar for the first card, second one is similar as well. What about number 3, card 3? What do you think? Pause the video, think about it. All right, so hopefully you unpaused it and you realize that these are neither congruent or similar. Why do I say that? Well, the angles, right? The angles look a tad bit different, right? So the angles look different. The first trapezoid seems to be squished a lot more, while card or the figure F seems to be stretched out a little bit further. Okay, so I would say neither. Card 4. Let's see. That's weird. This is the same exact object. You notice that? So similar, congruent, neither similar or congruent. Well, these are both congruent, right? Because you have side, side, side. I mean, every single part of this, right? So these are congruent. These are congruent. They are exactly the same dimensions for every corresponding part. Okay. So yeah, those would be congruent. Card 5. Are their angles? Their angles appear to be congruent. Their sides are different. Right? I would say similar. They look similar. Definitely not congruent. But I would put a strong indicator that that's probably similar. I mean, I would like to know the other sides, right? To make sure that they went through the same scale factor, right? If they didn't go through the same scale factor, then I would probably notice the angles being different. But since the angles are all congruent to each other, at least the corresponding angles are congruent to each other, I would definitely say similar. If you look at it, they also look very similar when you stare at them. All right, card 6. What do we got here? What do we have? This side is congruent to that side. This angle is congruent to that angle. This side is congruent to this side. They're both right triangles, right? We don't necessarily have the hypotenuse here, but we have side angle side. So that means that these two are congruent. Okay. And yeah, so that was the card sort. Nice quick rundown of similarity, congruency, or neither, right? All right, 6.3. One figure is similar to another if there is a sequence of rigid motions and dilations that take the first figure so that it fits exactly over the second. Okay, so for example, sliding over the smaller triangle with a translation, and it fits nice and snug over the first figure. Okay, so notice this triangle ABC is similar to triangle FDE. So that is a symbol for similar. Squiggly, okay, is similar to. So let's see if we can start applying that here. Are the triangles similar? Okay, so let's take a look and go ahead and see if we can make this similarity statement. So notice all the angles are congruent. Okay, so that's probably a good indicator right there. And let's see what else we have. AB is parallel to QR. Okay, so this is parallel to that. Well, what's scale factor? Let's see. Write a sequence of transformations. So we got dilation, translation, rotation, reflection. Okay. Well, if we're obviously going to have to use a dilation, right? So who's the figure and who's the image, right? So I'm going to assume that triangle ABC was the original figure, and then we do some kind of translation to get to triangle QRT. Okay. So we have 15 here turning into 6. So we have 15 times some scale factor to get us 6. I'm going to apply the division property. They're both reduced, right? They both have the same common factor of 3. So that's 2 3s and 6, 5 3s and 15. So it looks like my scale factor is 2/5 here. Okay, so now that I know that, I can say that we can dilate. So first things first, dilate triangle triangle QRT with scale factor of, actually we're going to have to do reverse of 2/5, right? Because that'd be 5/2. Now let me explain. To get from the larger triangle to the smaller triangle, you had to multiply by a scale factor of 2/5. But remember, we're trying to reverse this. We're trying to get the smaller triangle to map perfectly onto the larger triangle. Okay? So we're actually trying to reverse what happened. So that's why I'm dilating by 5/2, right? That is the reverse. Okay? So if we do that, okay, and then probably with center of dilation at point, I'll just say R. Okay. And then, so that'll give me something like, actually, let me draw this a little bit better here. Actually, better yet, let me trace over what I wanted to get so we can see this line up perfectly. If my pen decides to, okay, my pen's going to be difficult, so I'm just going to ignore my pen. There we go. There we go. All right, so if I dilate with a scale factor of 5/2 at R, I'm going to get something like that. Okay. And then I'll tell you what, I'm going to move down my answer for number 1. Okay. And I'm just going to say, after the dilation, I'm going to just translate over to where point R maps onto B. So translate triangle Q prime r prime t prime along line RB. Okay, what is that going to look like? That'll look like this. And there you go. So that would be a sequence from one to the other, okay, which proves that these two triangles are similar, okay. Write a similarity statement for about the two figures and explain how you know they are similar. Okay, so number 2, I'll write a little further down here. I know that AE is similar to QT, right? That's here to here. I also know that EB is similar to TR. They're both the hypotenuse, right? So EB is similar to TR. And how do I know that? Since they correspond and apply the same scale factor. Okay, so when they were getting smaller, right, the scale factor was 2/5. If you go reverse of that, it's 5/2, right? Okay. So compare your statement with your partner's statement. Okay, so if you got anything different, let me know. But that would be pretty decent answers right there. Okay, so in summary, if one figure is similar to another, okay, there is, and don't forget the symbol for similar, looks like that, right? Squiggly line. So one figure is similar to another if there is a sequence of rigid motions and dilations that takes the first figure so that it fits exactly over the second. For example, right, we have this smaller triangle here. Looks like it's dilated and then looks like it's reflected across, right, to map onto the smaller triangle. So they're trying to prove to us here, or it looks like they said a rotation. Okay, so they rotated 180 degrees, I assume. Okay, so they're saying that triangle DHF, which is the smaller one, is going to be similar to triangle EHG. Okay, so you can use rotations, you can use reflections, translations, rotations, reflections, which are all rigid, but there definitely has to be a dilation. Make sure the dilation is applying the same scale factor to every single side length, right? And remember with dilations, angles stay the same, right? Which is probably a good indicator that you did it correctly, and you probably will also visually see similarity as well. Okay, have a beautiful day.